So we found we completed the table and we found the vertex transitive graphs that you can complete.
Yeah.
Yeah. So for B, because you already did A pretty much. I guess for B, there's there's a square with the diagonals with its diagonals, and basically any even-sided polygon with the diagonals connected.
Okay, let's just think about that for a minute. So you had
You want to draw
Can you?
the
diagonal.
these two arbitrary points, connect these two.
Okay, that's
Like,
this is what's called a complete graph.
Yeah, complete graph.
Actually, this is not an answer to B, because if this is the center, say, then the vertices distance 1 are all neighbors. So in fact, the this one corresponds to a triangle. Okay, you're drawing something?
Sorry, we are facing some issues on the phone.
alright.
Sorry, could you explain that again?
I was just saying that, in fact, the square with all its triangles, or a complete graph, or a tetrahedron, is not an answer to this one, because the edges are all, the vertices all have edges between them here. But I think probably most of your others are. So what other examples did you have?
Wait, so if you add in the center, wouldn't it have?
Sorry?
So if you add in the center for B, wouldn't it have wouldn't it be like?
Well, yeah. So you B, then you add the center. It should look like that. So the neighborhood of the center looks like that.
Yeah.
Right, so you could have I don't know, like the infinite tree with.
Yeah, infinite tree is one example. A cube is a finite example.
Right. Yes.
Oh.
Alright.
I think a dodecahedron is another example.
So would the complete graph be a solution to C?
The C. Yeah, that's an answer to C.
Okay.
And that's the only answer.
Why is it the only answer to C?
Well, because it can't grow beyond this, right? As soon as we try to add another vertex, this one now has 3 neighbors.
Yeah, answer.
So for this one, we can't grow any. It can't grow any further.
So again for B, why is that complete graph not?
Why is the complete graph not?
Yeah.
Everybody's difference you connect it.
Okay, so that's what if this is the center, that's what the neighborhood has to look like, but the complete graph is like this.
Oh yeah, okay, yeah, that makes sense. Yeah.
And what about D?
Yeah. We didn't find any.
Didn't find any. Right. Well, that's good, because there are none. This one does not extend.
Yeah.
Did you think about showing that it doesn't extend?
Oh yeah, because if we have points A, B, and C such that B is connected. Wait, how do I draw?
You can draw the whiteboard here.
Yeah, what? Were you going to draw something?
Yeah.
Just can you see the whiteboard?
Yeah.
Yeah, so if we have like, I
Use
believe,
the pen.
oh, innovative technology. So these are 3 points. Let's just call them. Wait, oh my god. That's A. This is B. This is C, right? And then let's just connect these, and then there's gonna be an O here, right?
Mm-hmm.
Which connects to all 3.
Yeah.
So it's required that C must also be connected to 3 others. So let's connect it to arbitrary point P. But then since it's for it to be vertex transitive, like either BP or OP must be an edge, but that would make them have a degree of 4, so it just wouldn't work. Is that correct? Or did I miss something?
Yeah, that's right.
Alright.
Yeah.
Alright.
Can I write on this screen?
You should be able to, yeah.
Doesn't seem to be working.
Is there like an annotate? If you could annotate.
Oh yeah.
Oh, good.
Yeah.
Now you might try this one. Maybe not right now, but that's another one to think about. So now you want to add another vertex. If you call that O, you want to see if that works. And what about the table, the multiplication table for the group of symmetries of the square? What did you get?
Do you want us to?
Alright.
Yeah, can you write it on the screen?
Yeah.
Alright. Oh wait, are there straight lines?
Well, you don't have to actually draw a table. Yeah.
Or like,
Line lines.
line.
So, that's not.
It is now.
It's like 5.
Yeah.
9.
Oh, that's fair. We'll just make 2 of them.
Yes. Just
Right.
Too much emphasis on the actual table.
yeah. Just writing. It's clear this in the writing.
You have a pen.
Oh wait, I do have a pen.
It's clear in writing. Sorry.
So which one goes first? Does the
what's your?
yeah, okay, so R1, R2, R3, and this is S1, S2, S3, S4. If this goes first, this is S1.
Oh, your handwriting is so bad.
Because it is a laptop screen, unfortunately. I'm not used to this. And then I go for S1. I got this was S4.
Yeah, I got that too.
And then
S4, S1, S2.
Yeah, S1, S2, S3, and then S3.
Yeah, S3, S4, S2, S1,
S4, S1.
Okay, did you do the whole table, the 8 by 8?
Yeah, we did.
Yeah.
We just did put 9 rows of
and
9 columns because.
Yeah, and then for the. Yeah, And then the rotation one we already did. The rotation one just it's basically additive. The oh wait, wait.
Try to speak up. You might not be able to hear you.
We really did like the R1 R's by the R's.
Yeah. S4 and S1. That's a bit messy. Okay, so then what happens if? Oh wait, we do need.
You do need 9 rows.
Yes, we
and
do
9
need the 9
columns.
rows. Wait, the power of eraser.
You could have cleared it at the start.
Yes, but I am bad.
Okay.
Yeah, so this is E. R1.
No, this is what it is.
R2, R3. Yeah.
Yeah, I prefer you didn't do it that way.
Yeah.
Just live.
Because what I'm trying to get at is there's a pattern.
Yeah, there is.
Where do you want to get it?
Secure all
Clear
drawing.
drawings. Yeah, can you do it?
Yeah, can you do it?
Yeah.
Wait, so do you want it like E, R1, R2?
Yeah.
This is horrible to draw.
Yes, exactly.
Perhaps don't worry filling in all of the
Yeah, okay.
table, because what I hope you've seen is that comes into 4 blocks. So there's R here, and
Yeah.
S and R.
And then it's back to R, yeah.
Yeah.
And what I wanted to point out is that this is the same as addition modulo 2, right? Or
Yeah.
or so that's addition mod 2, and it's the same as if we have multiplication with 1 and minus 1, right? Or the product of two negative numbers is positive, and so on. What I wanted to point out is that this is this sort of pattern is how we break down the symmetry groups into smaller pieces. So the symmetry group of a square can be thought of as factoring into 2 pieces. So there's the piece that's the rotation, and then there's a quotient by that. So there's a piece that's the rotation. Right, sorry, I didn't mean to do that. Yeah, perhaps I guess that's right. So there's a piece that there's the rotation, and then when we quotient by that, we get this sort of pattern. So the group of symmetries of the square comes in these 2 parts. There's the rotations, and then there's the reflections give this this sort of pattern.
Yeah.
And that's that sort of factoring of groups is a method for analyzing them or studying them. I don't know that we're going to get into that too much this week, but that's just something that I wanted to point out, that that's a very important part of group theory and the study of symmetry, this sort of factoring of groups. Okay, so what next? Yeah, can you go to a new screen?
You can use your whiteboard if you want.
Yeah.
Yeah, okay.
Okay. Let me.
Why don't I suggest some others to look at? This was one that I suggested already. Then maybe I think we can try for longer and longer lines. Which ones extend? So we want to add a vertex. And see whether we can extend that to a vertex transfer graph. Then beyond that, I would maybe just play with some examples yourselves. Just try different examples and see if you can extend them. Well, perhaps let me give one more. Just try the polygons.
Triangle pattern.
Which of those extended, then perhaps play with some examples. Okay. I don't know that I wanted to say much more at the moment, other than just get you to keep looking at those examples. Yeah, do you have any questions?
So the triangle one would be the tetrahedron.
That's right. And doesn't that one I think doesn't extend any further for the same reason as C. Right. So there's a pattern there that you might be able to see.
No, it's like how much you've known about all this stuff. This what's unknown. What's known.
What?
Perhaps while you're thinking about that, I'll send the link to the webpage where you can find the seminars and like it.
Okay. Alright.
Aren't you curious which one of these, like if there's it's unknown, because there's an unsolved version of this?
Yeah.
Well, I assume they're all unsolved, and then I will solve them myself and see.
It's what you'd assume like these are all known,
Yeah, maybe.
but what if one of them is not known?
Well, if it's not known, then we're helping with the research, you know.
Yeah, but don't you want to know which ones?
No, not really. Just
I'm pretty sure the polygon stuff. Because you get like massive degree in the center.
yeah. If you go for the longer and longer ones, you can use a similar argument where,
Oh yeah, I thought I covered it.
yeah. So then there's this connected to 3. There must exist like this. What does this have degree of? Let's say this degree of n. That's connected to 3, so there must be n minus 3.
I'm sure you could think of some more questions.
And then so just go down. There must be like a certain amount of them connected and whatever. So it just like doesn't work. Some polygons. Well, that's a good question. Are there any known graphs that require infinite that their solutions are only infinite?
And you can answer them.
Yeah. Wait. How do I address him?
So
Professor Willis.
Sir. Wait, sir. Are there any known graphs that that the only solutions are infinite? Basically, I don't know how to describe it, but
Sorry, what was that?
are there any graphs that their only solutions are infinite? Like, how do I describe it?
Yes, there are.
And how would we determine if a graph only has infinite solutions?
Well, this is a question we'd like to know the answer to.
Oh, that's interesting. Thank you, sir.
wait, what did the repeat?
It's a question you would like to know the answer to. So, so
you can't determine.
So we can do certain small ones. We've done those by hand, and we're trying to develop a computer algorithm to do a search. But so the question is, given the finite graph, which of them extend to a vertex transitive graph? And I suspect that most do not. But yeah, we need to. If that's the case, we'd want to have some way of quantifying that. What do we mean by most? But we also want answers to the sort of questions that you're asking. Which ones only have finite extensions? Which ones only have infinite extensions? And which ones have no extensions? The ones we're really interested in are those that have infinite extensions. And beyond that, the ones we are interested in are those where the group of symmetries is not discrete. So perhaps I'll say something about that. And then I'll have to go to the seminar. So take something like the, well, let me just go back to these two examples. So we had the integer lattice, and then a tree where every vertex has 4 neighbors, which I'll draw like this now. And so on. Now, I said this one has translations, rotations, and reflections. Then, but now let's suppose we take some vertex, and now we ask ourselves, what are the symmetries that fix this vertex? Okay, so we can't translate anymore. But what can we do? Well, we can rotate. We can rotate through 90 degrees, and we can reflect in axis. So in fact, this one, if we're fixing a vertex, the symmetry group is the dihedral group. Fixes a vertex, or a copy of the dihedral group fixes a vertex. Perhaps I should put it the other way, another way around. The subgroup fixing a vertex is finite, and the word used is isomorphic. So if you write down the multiplication table, it's the same as the dihedral group of the square. It's just the same rotations and reflections. But now, what if we fix this vertex? We fix the vertex here. What can we do? Well, we can rotate around, and we can reflect, but we can do a lot more. We could, for example, fix everything here, and then just say flip those 2 branches. Or we could even fix everything in a bigger tree and flip. Well, we can swap around these branches. Right. So the subgroup fixing a vertex here is infinite. And these are the ones we really want to find. Those where the symmetry group is really very large, so that if we fix a vertex, we still get an infinite group. Okay, and there are trees, and there are other examples we know about, but we don't know if we've found all of them.
Right.
All right, so yeah, so infinite extensions, and it would be interesting if there are some graphs that only have an, if we can say what graphs only have an infinite extension. All right, any more questions?
No, not really.
All right.
Okay.
No, not much.
No? Okay. I sent a link to a web page, and I forgot to say there's another tab that you should look at. Let me just send emails on that as well. Yeah, so there's a link to the web page that I sent to Michael, and there are videos, and there's also some drawing tools that are available on that web page. It's not very well developed yet, but we're just starting out with it. We're trying to get some more sophisticated things going. Yeah, there are more links that I'll send you later in the week.
Right, thank you.
All right.
Okay. Shall we stop there, because I'll need to go home to get to the seminar fairly soon, and I'll answer any questions you have, or explain some more things if you want me to go through more things. But I think you've got enough to play around with or think about before seminar.
Yeah.
That's right.
Thank you.
Thank you.
Okay. So we've got two speakers in the seminars this afternoon. The first one is from Ohio State University, and the second one is from the Technion in Haifa, in Israel. You can't be expected to understand anything much of what they say, but you'll maybe get some impression from it, and you might not want to stay very long, but at least you'll get some impression from the.
Yeah.
And if you have any questions about them, you can ask me those later as well.
Yeah, it'll be like a fresh experience.
That's true.
Sorry, what was that?
It'll be like a new experience, even if we don't get much.
I still didn't quite catch it.
It'll be a new experience, even if we don't understand much. Because university seminars are different from what we're used to.
Yeah, they certainly are different from what you're used to, and the speakers will be assuming much more than you know, and most of the people in the audience won't be familiar with a lot of what they're talking about, so I have to explain that. But even so, it'll be several steps beyond where you are at the moment. All right, shall we still do that and then perhaps meet up again tomorrow?
Yeah, that sounds good.
Yeah, that's fine.
Okay, what time tomorrow?
Same time, maybe?
At 10 o'clock?
Yeah.
Yep, okay. All right, well, I'll see you then.
Yeah, see you then. Thank you.
Yeah, thank
Okay.
you.
Right.